Welcome to the deep dive. We're jumping straight into something pretty fascinating today, the world of dental materials.
That's right.
You sent over a really great video lecture and also a detailed PDF, both looking at the physical and chemical properties of the stuff dentists use.
Mm,
So our goal here is basically to unpack the key principles, how these materials actually work, especially inside the mouth, which is a pretty challenging place for any material.
it really is. Think of this as a kind of shortcut to understanding the science behind, well, everything from fillings to crowns.
Exactly. And this isn't just for dentists or students, right?
Absolutely not. If you're just curious about why your dentist picked one material over another or, how it's supposed to last, this should give you a really solid foundation.
We're aiming for those aha moments, focusing on the core ideas and how they apply in the real world without getting bogged down in like super technical terms.
Precisely. And the sources were great for that. The video, it had a nice conversational style, covered a lot. Bonding, diffusion, surface energy, wetting.
Micromechanical bonding, the older stuff, color, heat, even those electrochemical reactions.
Yeah, and the PDF kind of complemented that, gave
Yeah.
more concise definitions, classifications. Really useful.
So we'll try and blend those together, give everyone a comprehensive but hopefully digestible picture. Okay, so where do we start? It all comes down to how materials are held together at the atomic level, doesn't it? The bonds.
That's exactly the foundation. Everything about how a material behaves, its strength, its melting point, how it reacts, it all stems from the forces holding its atoms together.
Yeah.
We usually split them into primary and secondary bonds.
Okay, primary first. Those are the strong ones.
Those are the strong ones, yes.
Mm.
The internal scaffolding, you could say.
Yeah.
Three main types there. First, ionic bonds.
Right. The video used table salt, NaCl, as the classic example. One atom gives an electron, the other takes it.
And you get charged ions, positive and negative, that strongly attract each other, like tiny magnets.
And the lecture noted these are actually stronger than covalent bonds, which is interesting. That strength, does that make them good for certain things in dentistry, like resisting pressure?
It can, yes.
Yeah.
That strong attraction makes them resistant to compression, being crushed, but they can also be a bit brittle. Next up is covalent bonds.
Okay, covalent. That's where atoms share electrons, right? Not a give and take, but sharing.
Exactly. They share electrons in their outer shells to become more stable. This is typical in polymers, plastics, a lot of organic materials we use.
And the third primary type, metallic bonds.
Metallic bonds, yeah. Found in metals, obviously gold alloys, amalgam components. The video described it well like cloud or gas of electrons shared freely among a whole lattice of positively charged metal atoms.
A sea of electrons, kind of?
Kind of, yeah. And these bonds are very strong, takes a lot of energy to break them. That's why metals are typically strong, ductile, and good conductors of heat and electricity. Those free electrons can move easily.
So those are the heavy hitters, the primary bonds. Then you mentioned secondary bonds.
Yes, secondary bonds. The key difference, like the video stressed, is no electron sharing or transfer. They're much weaker attractions.
Weaker how?
They're based on temporary or permanent fluctuations in charge distribution around atoms or molecules. Think van der Waals forces, hydrogen bonds.
Ah, okay, so more like fleeting attractions, not the strong handshakes of primary bonds.
That's a good analogy, yeah.
Yeah.
More like just standing near each other.
Sure.
These weaker forces are important for things like, say, the properties of waxes or how some polymer chains interact.
And the strength of all these bonds, primary and secondary, dictates whether something's a solid, liquid, or gas.
Absolutely. Water was the example used. In ice, strong-ish hydrogen bonds hold the molecules in a fixed lattice solid. Add heat, you give the molecules energy. Loosen those bonds to liquid water, add way more heat.
And they break free completely, flying around as gas or steam.
Exactly. The energy overcomes the intermolecular forces.
Oh, okay, got the bonds.
Yeah.
Now, how do things move around within these materials or environments? Diffusion came up next.
Right, diffusion. The video's ink and water example is perfect. It's just the natural tendency for stuff to spread out from where it's concentrated to where it's less concentrated.
Driven by the random motion of molecules, basically.
Exactly. And the rate, how fast it happens, depends on a few things. Temperature was a big one mentioned.
Higher temperature, faster diffusion.
Yep. More heat means more kinetic energy for the molecules. They move faster, bump around more, spread out quicker, like sugar dissolving faster in hot tea than iced tea.
Makes sense. What else affects the speed?
The concentration gradient, The bigger the difference in concentration between two areas, the faster the diffusion. Also, things like imperfections in a solid structure, like tiny cracks or gaps, can provide pathways, speeding it up.
And things that slow it down.
Bigger atoms or molecules find it harder to move, and stronger bonds holding the material together will resist that movement.
So ink spreads easily in water because the water molecules aren't rigidly locked, but ink wouldn't really diffuse into a solid block of metal because the atoms are packed tight with strong bonds.
Precisely. Very limited movement possible in a well-ordered solid.
Okay. Diffusion is spreading out. What about sticking together? Adhesion and cohesion.
Right. Two important terms. Cohesion is the attraction between molecules of the same stuff, like water molecules sticking to each other to form a droplet. It's the internal strength.
And adhesion.
Adhesion is the attraction between different types of molecules. So the ink sticking to the water molecules, or more relevant here, the glue sticking to the tooth.
The lecturer also mentioned adhesive and adherent.
Yes. The adhesive is the bonding agent itself, the cement, the glue. The adherent is the surface that sticks to the tooth structure, the ceramic crown, whatever it might be.
Got it. So for good adhesion, you need the adhesive to actually, spread out properly on the adherent surface, right? Which brings us to surface energy and wetting.
Exactly. Wetting is key. Surface energy is kind of like the surface tension of a solid. Some solids have high surface energy, think metals, ceramics. Their surface atoms have unsatisfied bonds and are eager to bond with something else, like an adhesive.
So high energy surfaces are easier to wet. The liquid adhesive spreads out more readily.
Generally, yes. They're more receptive to the liquid. Low-energy surfaces like Teflon or some plastics have weaker forces at the surface. They're less reactive, so liquids tend to bead up more. They're harder to wet.
And impurities, like dirt or oil, on a surface would lower its energy and make wetting harder.
Definitely. That's why cleaning and preparing the tooth surface is so critical before bonding. You need that clean, high-energy surface for the adhesive to wet properly.
Wetting itself is just the liquid flowing over and staying in contact with the solid.
Yet good wetting means intimate contact between the adhesive and the adherent, maximizing the area where those attractive adhesive forces can work. Poor wetting leaves gaps, voids, weak spots.
And we measure this with the contact angle, the angle the edge of a water droplet makes with the surface.
That's the one. A low angle, less than 90 degrees, means good wetting. The liquid spreads out because the adhesive forces, liquid to solid, are stronger than the cohesive forces within the liquid itself.
And a high angle, more than 90 degrees, means poor wetting. The liquid balls up.
Correct. Cohesive forces dominate. For dental bonding, we want a low contact angle, ideally close to zero, so the adhesive flows really well into all the microscopic nooks and crannies of the prepared tooth surface.
Gets into everything for a good grip. Now, speaking of grip, before modern adhesives, how did things like old crowns stay on? The video mentioned micromechanical bonding with things like zinc phosphate cement.
Ah, yes, the pre-resin era. Back then, retention wasn't really chemical, it was almost entirely mechanical.
How did that work?
Well, the dentist would prepare the tooth surface, maybe making it slightly rough, and also the inside of the crown. The cement, when it was mixed in fluid, would flow into these tiny irregularities, these undercuts on both surfaces.
So it flowed into the microscopic pits and grooves.
Exactly. And then when the cement set hard, these little projections of cement acted like tiny keys and tiny locks, physically interlocking the crown onto the tooth.
So not a true bond like we think of today, more like mechanical friction and interlock.
Precisely. The PDF notes these cements didn't really chemically bond. Success relied heavily on the preparation shape and capturing those surface details for the cement to flow into.
Interesting stuff. Okay, shifting gears to something patients really care about, how restorations look. Color matching.
Hugely important. Mimicking the natural tooth is the goal. The video talked about how light interacts with enamel, reflecting, refracting, absorbing, transmitting. That complex interaction gives us the color we see.
Right, and it mentioned enamel's refractive index, 1.65, which affects how light bends passing through it.
Yep. Then the lecture broke down color using the Munsell system. Hue, value, and chroma.
Okay, hue is just the basic color, right? Like red, yellow, blue. The video mentioned the A, B, C, D shades in dentistry corresponding to reddish brown, reddish yellow, gray.
Yeah, reddish gray, yeah. Those are the basic families of color we see in teeth.
Then value. That's lightness or darkness.
Exactly. It's the grayscale, from pure black to pure white, 10. This is often considered the most critical dimension for matching teeth. Getting the lightness right is key.
And the video made a crucial point. You can always make a crown darker, lower the value, by adding stain, but you can't easily make it lighter increase the value once it's fabricated.
A really vital clinical takeaway. It means you need to be very careful not to pick a shade that's too dark initially. That's why many modern shade guides are arranged by value, from lightest to darkest, to help prioritize getting that right.
And the third part was chroma.
Chroma is the saturation or intensity of the hue. Like, is it a pale, washed-out yellow or a really strong, vibrant yellow? Scarlet red versus pale pink.
Got it. Hue, value, chroma. But picking the right shade isn't always straightforward. The video mentioned observer effects.
Oh, yes. Our eyes can play tricks on us. Low lighting obviously makes it hard to judge color accurately.
Staring too long at one color, like the patient's red lipstick.
Exactly. Your eyes' receptors for red get fatigued, and you start to perceive the complementary color, green, more strongly. So you might incorrectly choose a shade that looks slightly greenish to compensate when it's really not. Short glances are better.
Looking away at something neutral, like a gray card, helps reset your perception.
It does. Also, the background color matters. A bright blue patient bib might make you perceive the tooth as slightly more yellow. Blue's complement.
Wow. And then there's metamerism. That's a big one.
That's the phenomenon where two colors match perfectly under one type of light, say the dental chair light.
But look completely different outside in natural daylight or under fluorescent office lights.
Precisely. Because different light sources have different amounts of red, green, and blue light in them. So the object reflects light differently depending on the source.
So the advice is to check the shade under multiple light sources, including natural daylight if possible.
Absolutely essential to avoid that metameric mismatch, where the crown looks great in the office but off somewhere else.
Fascinating complexity just in getting the color right. Okay, let's move to thermal properties. How materials handle heat and cold. Big issue for patient sensitivity.
A very big issue, especially with deep fillings close to the nerve, the pulp. You want to limit thermal shock.
So thermal conductivity is key. How well a material conducts heat.
Yes, and there are big differences. Metals are generally excellent conductors. Think gold, amalgam, ceramics are less conductive, and polymers, like composites, are relatively poor conductors, more like insulators.
Which explains why a big metal filling might cause more sensitivity to hot coffee or ice cream than a composite filling would.
Exactly. The metal transmits that temperature change much more efficiently to the underlying tooth structure and potentially the pulp.
The video also mentioned thermal diffusivity. How is that different from conductivity?
Diffusivity is more about the speed at which a temperature change propagates through the material. High conductivity means heat travels easily. High diffusivity means it travels quickly. They often go hand in hand, especially in metals.
Okay, and then coefficient of thermal expansion, alpha.
Right. That measures how much a material expands when heated or contracts when cooled for each degree change in temperature.
And why does that matter?
Because the tooth itself expands and contracts with temperature changes. If your filling or crown expands and contracts at a different rate than the tooth,
you can get gaps opening and closing at the margin.
Precisely. That movement can break the seal, leading to microleakage fluids and bacteria getting in, causing sensitivity or recurrent decay. Ideally, you want a material with a thermal expansion coefficient very close to that of the tooth.
And heat capacity was the last thermal point. Energy needed to change temperature.
Yes. How much heat energy it takes to raise the temperature of a certain amount of the material by 1 degree. Metals like gold have low heat capacity. They heat up and cool down quickly. Combine that with their high conductivity and diffusivity.
And you see why pure gold isn't always ideal near the pulp. It offers very little thermal protection compared to, say, dentin itself.
Correct. It transmits temperature changes very readily.
Okay, last major area, electrochemical reactions. Thinking mainly about metals here, like amalgam or gold alloys, tarnish and corrosion.
Right. Tarnish is the easier one. It's just a surface discoloration, like silver tarnishing. A thin film of oxides, sulfides, chlorides forms on the metal surface.
Usually just looks bad, not necessarily damaging the structure.
Not initially, no. It doesn't involve significant loss of the metal itself. But, the video pointed out, it can be a precursor to corrosion.
Corrosion being the more serious one.
Yes. Corrosion is the actual degradation, the deterioration of the metal through chemical or electrochemical reaction with its environment. It can involve material loss and potentially weaken the restoration over time.
And it happens because the mouth is, well, wet and full of chemicals.
Exactly. Saliva acts as an electrolyte, a conductive medium. You have water, oxygen, chloride ions, acids from food and bacteria. It's a corrosive environment. For metals, it's often an electrochemical process involving tiny electrical currents.
Which leads to that other thing mentioned, galvanic shock.
Ah, yes. That happens when you have two different metals in the mouth, say a gold crown touches an amalgam filling. Because they're different metals, they have different electrical potentials.
And the saliva completes the circuit.
Like a tiny battery, a small current flows between the metals, and if that current is strong enough or passes near the pulp, it can stimulate a nerve and cause a sharp, sudden pain.
Ouch. So things like sulfur in food, acids, even just saliva itself can contribute to both tarnish and corrosion over time.
They certainly can. And that tarnished layer, while sometimes protective, can also sometimes trap corrosive agents against the metal surface, potentially accelerating deeper corrosion.
It really shows how challenging the oral environment is for any material we place in there.
It absolutely does. Durability, biocompatibility, aesthetics, handling properties, thermal behavior, electrochemical stability. Dentists have to juggle all these factors when choosing a material.
Wow, okay, that covers a huge amount of ground from those sources. So just to wrap up for everyone listening, the key things to take away. You've now got a much better handle on the basic bonds holding materials together.
How things like ions or molecules can move around through diffusion.
Why getting liquids to wet surfaces properly is so vital for bonding.
The science behind matching colors, which is trickier than it looks.
Why some materials feel hot or cold more than others.
And how metals can interact chemically in the mouth over time, leading to tarnish or even corrosion.
It really makes you appreciate that choosing, say, a filling material isn't just picking something off a shelf. There's so much science packed into that decision.
Absolutely. And think about how things you do every day, what you eat, drink, even the temperature, can interact with those materials in your mouth.
Definitely gives you something to chew on, so to speak. So hopefully this deep dive gave you a solid foundation. If, any part of this really caught your interest, maybe the color science or the electrochemical side, definitely explore it further.
Understanding these basics really does empower you to understand your own dental care better and appreciate the complexity involved.
Well said. Thanks for taking this deep dive with us.